Welcome back to the NMR Challenges series. In the previous video, I provided this NMR challenge for you, and today we are going to explain the solution step by step. If you have already solved it, then you can match your answer by the end of this video. So let's start today's NMR challenge.
Here is our second NMR challenge. We are going to determine the structure of this compound having molecular formula C4H10O1. While determining the structure of this compound, we will learn how to calculate the index of hydrogen deficiency, how to interpret 1H NMR, and what is and how to interpret 13C APT NMR, and how it is different and better than 13C depth 135 NMR. So here is the 1H NMR of this compound, and this is the 13C APT NMR. Before solving this structure, we will again revise those steps which we learned in the last video. So it's better to revise each time so that we will never forget those chemical shifts values. And here are those steps. So first step is calculating the index of hydrogen deficiency, which is also known as degree of unsaturation, and this is the formula. So this formula is 2 multiplied by number of carbon atoms plus 2 plus number of nitrogen atoms minus number of hydrogen atoms minus number of halogen atoms divided by 2. So the value gives number of pi bonds or rings, or it could be both. If this value is equal to 5 or greater than 5, then we can blindly say that it has one benzene ring, and this benzene ring will correspond to the 4 value because it has 3 pi bonds plus 1 ring. Then we will see 1H NMR, and as we said that number of signals is equal to the how many types of protons are there. Splitting patterns will give us information about the number of neighboring protons or substitution pattern on the benzene ring. So here is the splitting pattern formula, n plus 1, where n is equal to the number of adjacent protons which are equivalent. And for determining the substitution pattern on the benzene ring, we should also know the J coupling value. So we will learn when we will have those kind of problems. So here we are just focusing on the aliphatic types of compounds so far. And 1H NMR chemical shift values is also very important to understand shielding and deshielding of the protons. As I told you, primary carbons, hydrogens coming in the shielded region from 1 ppm to 1.2 ppm. Secondary carbon hydrogens are slightly deshielded as compared to the primary, and tertiary hydrogens are slightly more deshielded from 1.4 ppm to 1.9 ppm. And we also learned that when methyl is attached to the ketone, then it comes from 2 ppm to 2.6 ppm, and it is quite similar value for methyl attached to the benzene ring, such as in toluene. So it is also coming in the same region. Acetylene protons is slightly deshielded as compared to the methyl attached to the aromatic rings. It comes from 2.5 to 3 ppm. This is very interesting value. When oxygen attached to the carbon, then hydrogens are coming around 3.5 to 4.5 ppm more often, and it could be higher also, but usually you will see in this range. And when it is attached to the nitrogen, then it can come from 3 to 4 ppm. We also learned that hydroxy and amines protons are acidic, therefore they can undergo exchange from one molecule to another molecule, therefore their values are not fixed, and it is coming from 1 to 5 ppm. The aromatic protons comes from 6 ppm to 8.5 ppm, sometimes overlap with the alkene protons. This depends on the nature of the alkenes. Aldehyde protons comes from 9.5 ppm to 10.5 ppm, but carboxylic protons always comes after 10 ppm to 13 ppm, and it is slightly broader signal. So we should remember these values because it is very important to determine the structure of the compounds. Then the third step is 13C APT NMR. So we will look 13C APT NMR, and we know that this NMR gives all kind of carbon signal, but in 13C depth NMR we don't see signal for quaternary carbon, the carbon which doesn't have any hydrogen. It also tells us how many types of carbons are present in a molecule. And we also learned that methane and methyl peaks are 180 degree opposite to quaternary carbon and methylene carbon. So in this spectra which we are going to show here, the quaternary carbon and CH2 signals coming in the upward direction, or we can say in a positive phase, and methane and methyl carbon are coming in the negative phase. But remember that when you are solving in MNOVA or any other software, then you can change it. You can change this phase by yourself, and then it could be opposite. But here the NMR which we are looking, in that case we are following this pattern because those NMRs are presented in this way. It is also important to remember some of the chemical shift values for carbon. So here are some chemical shift value for the carbon. When it is primary, So it is coming up to 35 ppm. When it is secondary, it is slightly deshielded. Tertiary is coming maximum 55 ppm. When it is connected to the oxygen, then it comes from 50 to 70 ppm more often, but it could go to 90 ppm depending upon the structure. Acetylene carbon comes from 70 to 90 ppm, and benzene carbons comes from 110 to 170. These values for the functional groups is very important to remember. Ester comes from 165 to 175 ppm, but amides could be slightly lower than ester. It can be from 160 to 175 ppm. Carboxylic acid is slightly higher from 175 to 185 ppm. Aldehyde always coming in highly deshielded region from 190 to 200. Therefore, it is easy to distinguish between carbonyl carbon from ester or carboxylic acids. So first we will calculate degree of unsaturation. 2C plus 2 plus nitrogen minus hydrogen minus X divided by 2. So it will give you 2 multiplied by 4 plus 2 plus 0 nitrogen minus 10 hydrogen minus 0 halogen divided by 2. So the compound does not have any unsaturation. No unsaturation. Now we will look at the NMR. So let's see how many types of signals are there. So 1A, this is B, this is C, D, E. So it has 5 signals. It means it has 5 types of hydrogens. And if you look at the signal A, which is around 1 ppm, it is triplet, because you can see the zoom section of this is here. This is triplet, correspond to the 3 hydrogen. So this triplet indicates that N value is 2, and this could be methyl. So the neighboring hydrogens are 2. It means this CH3 is attached to CH2, something like this. So this is A type of proton. Now let's look at the B. B is doublet. You can see here it is doublet, and it is around 1.2 ppm. Doublet, integration value 3 hydrogens. So this doublet means there is a 1 hydrogen in the neighbor, and this is the methyl signal. So this methyl group is attached to the carbon having 1 hydrogen, something like this. So this is the B type of hydrogen, and there are something like this in the molecule. Now let's look at the C. C, this is the C signal, and C is coming around 1.48 ppm. This is multiplet, and it is correspond to 2 hydrogen. So what does it mean? It means that this is hard to determine N value. We can't determine the N value in this case, but we can say that this is CH2, which is attached to something here, something here. If we try to combine this information with this information, then we can say that maybe this CH2, one side is CH3 and another side is hard to say. We don't know what is on the other side of this CH2, but it could be something like this. So this could be C type of proton. Now look at the signal D. If you see, there is a asterisk mark which is saying that this is exchangeable hydrogen, which means that this is corresponding to hydroxy group, because we have one oxygen in the molecular formula. So probably this signal, which is around 1.5 ppm, which is broad signal, and integration value is 1 hydrogen. Integration value is 1.5, so you can round off to one hydrogen, and it indicates that this could be OH. And there is no splitting because this is exchangeable, moving from one molecule to another molecule, therefore it is not showing any splitting pattern. So the compound having one hydroxy group. Now let's look at the E signal. So E is coming around, let's say 3.8 ppm, and it is, if you see this splitting pattern, 1 2 3 4 5 6, so this is sextet and corresponding to one hydrogen. So it could be something like this. This hydrogen is attached to CH3 on one side and another side CH2, because this gives N value is equal to 5. 2 hydrogen with from this methylene and 3 hydrogen from this methyl group. So it could be E type of proton, but we don't know exactly what are the other substituents. So let's combine all these informations which we are getting from 1H NMR. So here are these informations. So the A type of proton is connected to this CH2. There is one hydroxy, and this B type of proton is connected to this CH. And so this C proton is connected to A, and this E proton is connected to the B. So therefore there are some common informations, and we have to remove those common informations, or we can say we have to combine those common informations to bring it to the one level. So let's combine this information. So you can see that this information and this information is same, so you can remove one of them. And here this information and this information is same, so you can remove this one. So just combine these two information and see what you will get. So you can put here CH3. So this is the A proton which is connected to the C, and this one is E type of proton and which is connected to the B, and you can put on this hydroxy group. So this is the correct structure of this compound. Oh, it's great. We determine the structure just by 1H NMR without looking at the carbon, but we can use this carbon NMR to verify this structure. So let's look at the carbon NMR. So there is one signal, downward signal around 70 ppm. So we know that downward signal belongs to CH3 or CH. So this is in the D-shielded region, so this is probably CH, and it is close to 70, so it is most probably connected to the hydroxy group. And you can say that this kind of functional group is present in the molecule. This signal belongs to the CH2 because it is in the upward direction. And now there are two more signals, and we are sure that this is in the shielded region, so it could be CH3 for sure, but this could be CH3 or CH. We are not 100% sure, but it looks like it could be CH3, but let's say we don't know exactly the signal is CH or CH3. So from this 13C APT NMR, we get the information that the compound containing this group 1 CH2, 1 CH3 and CH3 or CH. So if you look at this structure, so this hydroxy connected to this carbon, so it means this 70 ppm signal belongs to this one. And there is one CH2, yes, there is one CH2. There is one methyl, yes, there is a one methyl. And now we can completely agree to the point that the compound containing another methyl group, not CH. So there is another methyl group. So this signal belongs to the methyl group. So hence we can say that there are two methyl group, 1 and 2, which is A type and B type of protons. And then there is a one CH, yes, there is one CH and one CH2. So this is the correct structure of the compound. Okay, so from 1H NMR and 13C APT, we can clearly say that this is our correct structure. But for our curiosity, let's do back testing for the splitting pattern. So this CH3, which is B type of proton, should show the must show the doublet. Yes, it is showing the doublet because of this proton. This neighboring hydrogen, there is one neighboring hydrogen, and this one E should be showing 3 and 5. So it should be showing sextet because it has N value 5. Yes, it is showing sextet. And now look at this one. this having 1 and 4, so it has 4 neighboring hydrogen, n is equal to 4, so this should be showing pentate. But this one, which is C signals, is showing multiplate. Why is it showing multiplate, not pentate? Okay, now look at this one. This having 2 hydrogens in the neighbor, and this is the A type of proton, so it must show triplet. Yes, it is showing the triplet. So everything is clear to me except this carbon. So what is the reason that this proton is not showing pentate but showing multiplate? So let's try to understand this one. If you look at this carbon, this is the chiral center and it is attached to 4 different groups. So when there is a chiral center and adjacent protons become diastereotopic. So this C type of proton, C protons are diastereotopic. Since C protons are diastereotopic, therefore we can write the structure like this, and then this CH3, this hydrogen, this is the E proton, and then it will be different. Let's say it would be further C dash and C. We can say that this is C dash and C, and this one is A type of proton. So there are n is equal to 4 neighboring. So this neighboring proton is split to pentate, and then this hydrogen further split this hydrogen, and then you will have like more multiplicity from HC signal, and then another HC prime signal will merge to give you multiplate. So this is the reason that CH2 of C type proton giving multiplate, because of the presence of the chiral center. Okay, now here is the challenge for you. You have to determine the structure of this compound, and if you look at the proton and carbon, then you can easily see that this compound is symmetrical. So try by yourself and let me know what is the structure of this compound, and we are going to solve this NMR in the next video.